All right, let's go over some thermochemistry notes. Day one. Starting from the top. Thermochemistry is the study of the energy changes of matter. So it's going to be energy changes of matter. Energy changes drive phase change, so solid, liquid to gas, solid, liquid, gas, and heating and cooling processes. Chemicals hold potential energy in their bonds and release or absorb energy during chemical reactions. All right, the law of conservation of energy. The law of conservation of energy states that energy can neither be created nor destroyed, but can be converted. It can be converted from one form to another. This is the first law, law number one of thermodynamics. All right, heat. Heat, which is represented by the symbol Q, not H, Q, is energy that is in the process of flowing from a warmer to cooler object. So this is a key idea in thermochemistry. Energy and heat flows from warmer to cooler objects. Warmer to cooler objects. When the warmer object loses heat, its temperature decreases. And vice versa, when the cooler object gains heat, its temperature increases. So think of a microwavable dish in the freezer. You put it straight from the freezer into the microwave, the object is cold. When it gains heat from the microwave, its temperature increases. Vice versa, if you leave the hot pot, say, out and it loses the heat, its temperature will decrease. All right, there are three types of heat transfers: thermal energy to internal energy. The first one is conduction. Conduction. And this is when two substances directly touch each other. So we have substance A or let's say we have a ball A and ball B, A and B. They directly touch in this space right there. Therefore, it is heat transfer by conduction. Now, the second type is convection. Convection. And this is transfer using density-driven flows, fluid movement. And this fluid movement, one example can be, say, water. Water H2O goes from a liquid state to a gas state at steam. So that's fluid movement. The third type is radiation. Radiation. And this is given off in the form of infrared radiation, like the sun. So our sun gives off heat. And this heat is delivered to us using radiation. All right, endothermic and exothermic. All processes occur in a universe with a system and surrounding. This is very important. System and surroundings. A system is one specific thing that you study. One specific thing. And the surrounding is everything else. Everything else. All right. So endothermic processes will absorb energy from the surroundings, and the container feels cold. Exothermic processes will release energy to the surroundings. The container feels hot. Okay, so I'll draw an example. Endothermic, you have a black ball object, and the heat from the outside will go inwards. All right. What that does to the environment is that the heat temperature, say it's say 50 degrees outside of here, 50 degrees Celsius. It's going to absorb that heat. That 50 degrees is going to be go inside the system, and so the surrounding temperature will be colder. Hence, the container feels cold. Vice versa, exothermic is where you have another black ball. Let's draw it a little separate from each other, and the heat is released from the ball outside to the environment. And what that does, if this is still 50 degrees Celsius, it'll increase the amount of heat because the heat from the system will go out to the environment. So it'll raise the temperature of the surroundings. Therefore, the container will feel hot. All right. So the exothermic Q value, heat is Q, and for exothermic, the Q value for exothermic will be negative. And so that means endothermic has a positive Q. And that makes sense because Q, the more heat you have, the more you keep in. So the more exothermic you are, which means you're giving away heat, the more negative your Q value will be. All right. Heat and temperature are not the same thing. Not the same thing. Temperature temperature is a measure of the average kinetic energy kinetic energy of the particles in a sample of matter. And this is important to know because heat and temperature, you can't confuse these two. They are two separate things. Separate things. They're not the same thing. All right. And one thing to note is that temperature will be measured in Celsius, degrees Celsius, or kelvins. K is kelvins. This is Kelvin. It's a measure of temperature, and this is Celsius. Celsius. Measuring heat. The amount of heat measured, or amount of heat required to raise the temperature of 1 gram of pure water by 1 degree Celsius. So 1 gram of pure water by 1 degree Celsius is defined as a calorie. Calorie. This is C. A kilocalorie, kilocalorie, is the food calorie with a capital C. So note that this C right here, is going to be a small c. This is going to be a big C. The SI unit of heat and energy is the joule. Joule, Joule. And that is capital J. 1 calorie will equal to 4.184 joules. All right. Thermodynamics of a heating and cooling and phase change. Specific heat. The specific heat, and this is the unit is going to be a C. Wow, quite confusing. C is the amount of energy required to raise the temperature of 1 gram of pure water by 1 degree Celsius. The specific heat of water is 4.18 joules per gram times degrees Celsius. 4.18 joules per gram times degrees Celsius. Let me write that a little apart. Joules per gram times degrees Celsius. Because different substances have different compositions, so say H2O has different composition versus carbon dioxide, CO2. So each substance has its own specific heat. H2O's C value, specific heat value, will be different from CO2's specific heat value. All right, and that is shown in the table below, how ethyl alcohol, aluminum, copper, and gold all have different specific heat values. Different. All different. Different. There we go. All right, let's calculate specific heat. The heat absorbed or released by a substance during a change in temperature depends not only upon the specific heat of the substance, but also upon the mass, m, of the substance and the amount by which the temperature changes. So temperature change is going to be change in temperature, so delta T. And so if you don't know, delta this is delta, and this means change in. All right, so we have three variables here. We have C for specific heat, delta T for temperature change, and M for mass. We use a calorimeter to measure the temperature change. The formula for specific heat, Q equals M times C times delta T. Delta T. Easy way to remember this is MCAT. MCAT. And this looks a lot like the actual word MCAT. So it is very easy to remember. Q, heat equals mass times specific heat times change in temperature. All right, and you're multiplying these together. All right, and one thing to note about delta T is change in temperature. Delta T, change in temperature, will always be equal to the temperature final minus temperature initial. All right, and this must be temperature must be in degrees Celsius. Degrees Celsius. All right. Let's take a look at this. Practice problem. How much heat is given off? How much heat? So you're looking for Q. Q is heat. Heat is given off when 869 grams of iron bar, that's mass, cools from 940 degrees Celsius to 50 degrees Celsius. So you want to be really careful here and determine which one is actually the temperature final and which one's the temperature initial. The temperature initial is you're going from 940 to 50, so this will be temperature initial. 940 is temperature initial. And 50 will be the temperature final, the temperature you're in at the end. So the way to calculate this, delta T, change in temperature, equals temperature final minus temperature initial. So all you're doing is 50 degrees Celsius minus 940 degrees Celsius. And in the end, that will give you negative 840 degrees Celsius. And that is your delta T, change in temperature. And keep that aside for now. You're looking for Q. And you have all your variables now. You have M, temperature, delta T, and then it gives you the specific heat. This is C of iron, which is 0.444 joules per gram times degrees Celsius. So now all you got to do is plug it in. Q equals MC delta T, which is MCAT, 869 for mass, grams, and then C, which is, it gives you 0.444 times delta T, which we figured out earlier, negative 840 degrees Celsius. Multiply all that together and it'll give you negative 343,394. And your energy is going to be, it's heat, so it's going to be in joules. And that is your answer. Now, if you look at the joules, oh wait, why is it negative? Wow. So this is important. What we talked about exothermic and endothermic earlier is that if the energy heat value is negative, it gives off heat. The system gives off heat. So the heat exits the system. Therefore, this will be exothermic. That means the heat during this reaction, the heat is given off. All right, let's reinforce our ideas. Phase changes. Phase changes occur when a substance changes from one state to another. That's like if you have a solid and you go to a liquid, or solid to a liquid and then you go to a gas, or you can go from gas to liquid, or you can go from solid directly to gas. These are all going to be phase changes from one state to another. For a phase change to actually occur, energy must be added or taken away. Energy must be added or taken away from a substance. And these changes are physical changes. Physical changes just mean that they don't change the chemical composition. If you have water, H2O, and it goes from a solid to a liquid, you're not changing the fact that this water molecule is still H2O. You're going to keep it as H2O, it's just in a different form. All right. Using this knowledge, we can mark either each of these six as endothermic or exothermic. What I said earlier, endothermic is heat enters. Heat enters. So endothermic enters. And vice versa. Exothermic exits. Exothermic exits. Heat exits. Let me write heat. Heat exits. All right. And so the first two letters are the same. That's an easy way to remember the difference between exothermic and endothermic. Using this knowledge, we can answer these questions. Number one, melting. If something melts, that means that it's absorbing heat. In order to melt, you're at a solid and you're going to a liquid, right? And by melting, you're going to increase energy. The more energy, so solid, liquid to gas, the higher up you are, the more energy you have. More energy. So if you're going from a solid to liquid, that's what melting is. Are you gaining energy or losing energy? Yes, you're gaining energy. Therefore, energy as heat enters endothermic. Vaporization. Vaporization is a process from liquid to gas. As I've said, the higher up you are in the phase, the more energy you have. If you're going from a liquid to a gas, are you gaining energy or losing energy? Yep, you're gaining energy. It is endothermic. All right, fusion. What could fusion be? Fusion is another word for melting. It's kind of blurry here, but I'm going to circle it in blue. You can see right here that fusion is melting. It's just another word for thermochemistry that fusion is going to be melting. And that gives you the idea that if melting is endothermic and fusion is the same thing, you know that melting equals fusion. So this is also going to be endothermic. Endothermic. Condensation. Condensation is when you go from a gas to a liquid. A gas condenses into a liquid. You're going down the scale this time. You're moving energy out of the system. It's exothermic. Combustion. If something combusts, that means it's going to catch on fire. Okay? Catch on fire. If something's on fire, is it warm or is it cold? Right, it's warm. It's going to be hot. That means there's a heat that exits the system. If wood burns, for example, if wood burns and it burns on fire, it's going to be hot. That means this is exothermic because heat is exiting. Heat is exiting. Exothermic. Not last one. Freezing. If you're freezing, you're going to go from a liquid to a gas. Okay? Liquid to gas. Once again, you're going down the scale. You're moving energy out of the system, so it's going to be exothermic. All right, that's it. Thank you.